Welcome to this demonstration of the SolidWorks Associative Interface for Abaqus. Here we're going to be studying a hose coupling. You can see in the model, the hose coupling is used to couple two hoses together through a latching mechanism shown in gray on the screen. The latching mechanism is moved 90 degrees and the green piece is pushed into the rubber gasket shown in blue for the seal. In SolidWorks, we can utilize configurations and cut the model to quarter symmetry so that we only need to analyze a quarter of the model. This will save us a lot in runtime. Once the model is complete in SolidWorks, we can then move on to Abaqus, where we can set up and run the analysis and study the stresses and pressure in the gasket. The SolidWorks Associative Interface for Abaqus is built right into the SolidWorks user interface. As soon as we link the Abaqus environment to SolidWorks, it's a click of the button in order to get the geometry from SolidWorks into Abaqus, where we can apply the loads and boundary conditions. We're going to work with the already set up model and just go through the setup. In the setup, we can see three different materials are used: polypropylene, rubber, and steel. If we look at the material model for the polypropylene, we can see it's an elastoplastic material with a predefined stress-strain curve. The rubber, we're using a hyperelastic material, and the steel is just linear elastic. Next, let's look at the contact setup. We'll utilize Abaqus's general contact properties, which will automatically find those faces that might touch during the analysis. Simple click. Next, let's look at the loads and boundary conditions. One side is fixed, while the other side is pushed in a little bit into the green piece is pushed into the blue piece a small amount. Additionally, we have applied X symmetry and Y symmetry to those quarter faces. Next, we'll mesh the model. In this example, we'll use brick elements to achieve good stress results as well as achieve good contact convergence in the model. From here, we can just go ahead and launch the job. In this example, we'll utilize 2 cores in the model, but we could utilize more cores if we had those resources available to us. Once the job is submitted, we can monitor the results as the model is running. But now we'll switch over to an already completed example. Here, the first thing we can look at is the von Mises stress, and we can animate this result to really see how the stresses develop as the latching mechanism is closed. Another result that might be interesting to look at is the plastic strain. Here we can see a large amount of plastic strain at that sharp corner there, which is caused right at the beginning of the analysis. Additionally, we may want to look at contact pressure in the gasket to make sure a uniform distribution of contact pressure is there to create an appropriate seal. Finally, we might want to look at the resultant force that it takes to close the actual latching mechanism. We can show both the stress plot as well as the resultant force plot at the same time and play through the results and see where the peak force actually is. What we can see in this example is that the latching mechanism has a little bit difficult time at the beginning where you get all that plastic strain in the sharp corner. So maybe a geometry modification might be necessary in order to reduce those forces required to close and minimize the plastic strain. We'll move right back over to SolidWorks and make the geometry modifications using the Filat Tool right within SolidWorks. Creating a fillet on those sharp corners is just a couple of clicks, and we'll go ahead and enter a dimension there. And from here, all we want to do is dump the geometry back into Abaqus. So we'll save the model, and then again, a single click is going to send the geometry right back to Abaqus for our analysis. The nice thing about the associative interface is all of our loads and boundary conditions were kept, so that all we need to do in Abaqus is simply remesh that part of the geometry that has changed. With a simple click, we can go ahead and remesh the part, And now we're ready to go ahead and submit the job again. We'll come back and just post-process the results. Here we can see both designs with the radius and without the radius, and we can see how the stresses develop within the model as the latching mechanism is closed. And the high stress in that polypropylene. Now it makes sense to also look at that equivalent plastic strain. We can see a significant reduction in plastic strain at the very beginning in that sharp corner because now we have that radius. We also may want to check the contact pressure of the gasket to ensure that we didn't really lose too much contact pressure. A simple click to adjust the scaling shows us that we really didn't have that significant a reduction in contact pressure, so we were able to maintain the contact pressure with our radiused design. Finally, we may want to also compare the forces required to close the latching mechanism. So let's go ahead and have a look at those plots. In this example, we can see the force is significantly reduced with the radius. Using Abaqus, we could easily go ahead and try different radiuses that are easy for production and figure out exactly which one minimizes the force. Thanks for watching, and contact your local reseller for more information.